Hi, in this video, I want to talk about what's typically taught in a Calc 2 class and also how you can prepare for and succeed in the class. A typical Calc 2 class in the US covers these three topics. Number one, integrals. This is easily the biggest part of the class. Of course, it will depend on the teacher or professor and the textbook, but I would estimate that anywhere between 40 and 60% of the class will be about integrals. The second topic is parametric equations and polar coordinates. These are alternative ways to represent points and curves on the plane. The third topic is sequences and series. Before I get into details, I want to talk about early transcendental versus late transcendental. The functions you're learning are generally classified into algebraic functions and transcendental functions. Algebraic functions include polynomials, rational functions, radical functions. Basically functions with sums, products, and powers. Transcendental functions include everything else. However, when a textbook says calculus early transcendentals or calculus late transcendentals, they are referring specifically to inverse trig, hyperbolic, exponential, log functions. A class or textbook that is calculus early transcendental looks like this, where the part with the cross shades represent transcendental functions. You're learning the calculus and you're applying it to all functions, algebraic and transcendental, as you go along. A class or textbook that is calculus late transcendental looks like this instead. You learn a lot of calculus up front, applying that to just algebraic and some trig functions. And then somewhere near the end, you start applying all of it to all of the rest of the transcendental functions before finishing off. These diagrams illustrate the Calc 1, Calc 2 sequence, all of calculus of one variable. So by the time a student finishes both Calc 1 and Calc 2, there's no difference between early and late transcendental. However, there is a difference at the end of Calc 1. Halfway through the sequence, the late transcendental people have learned more calculus, but they haven't applied any of it to inverse trig, hyperbolic, or exponential and log. The early transcendental people have applied all of that, but they know less calculus. No big deal, both will catch up at the end of Calc 2. But it does make a difference if, for example, you change schools and move between early and late transcendental. If you took early transcendental in Calc 1 and move into late transcendental Calc 2, or vice versa, there will be a need for some pretty important adjustments. Having said that, let's go back to the contents of Calc 2. The first part of Calc 2 is all about integration. Techniques of integration, applications of integration, differential equations, which itself is an application of integration. Techniques of integration refers to the mathematical methods to solve an integral. Given an indefinite integral, how do you make it into a function plus c? Or, given a definite integral, how do you compute its numerical value? A Calc 2 class would likely be teaching these techniques of integration. You'll also be learning applications of integrals. A typical way an integral is applied to real-life problems would be something like this. You start with some known formula, where normally you would just plug in constant values. For example, volume equals base area times height. You have a constant base area, you have constant height, you plug in, you multiply, done. But what if the base area is not constant? Let's take the solid you see on the slide. The base area is large at the top, but it's 0 at the bottom. Now what? Well, what we do is take one thin slice of it. Within that slice, the top base area and the bottom base area are so similar. They're different, but they're very close to each other. So we pretend that the base area is constant within that thin slice. So we take that base area, which we pretend to be constant, we multiply it by the tiny little height, we get the tiny volume of that thin slice. We add all the tiny volumes together, and the integral comes into play when we do the adding. Instead of adding them, we integrate. That's how an integral is typically applied to solve problems. Some applications you will learn in Calc 2 include volume, work, distance along a curve, which we call arc length, surface area, etc. Another application of integrals is to use them to solve differential equations. Now, this is still a calculus class and not a differential equations class, so the differential equation topics tend to be more limited to only these, basically separable and first order equations. By the way, to old people like me, this is kind of new. When I took Calc 2, differential equations were not part of it. They came in basically in the late 1990s in the colleges, and then in the early 2000s in the AP Calc BC curriculum, and since then it has become the standard. All that is the integration part of Calc 2, and like I said, it will take anywhere between 40% to 60% of the course. Part 2 of the course is parametric equations and polar coordinates. These are new ways of representing curves. Traditionally, we represent a curve by a function y equals fx. When we do that, we're limited by the vertical line rule, because a curve that does not meet the vertical line test is not a function. Any curve that does not meet the vertical line test will have to be broken up into smaller pieces so that each piece satisfies the rule. With parametric equations and polar coordinates, we're free from the vertical line test. All of these curves that you see on the slide have important real-life applications, and we can represent them using parametric equations and/or polar coordinates. The last part of a Calc 2 class is infinite sequences and series. A sequence is a list of numbers. In Calc 2, we tend to work with sequences that can be expressed as a formula in an integer n. For example, the sequence 1, 1/2, 1/3, etc. can be written as 1 over n as a general formula. A series is the sum of a sequence. If the sequence goes off to infinity, then the sum will also add all of these infinite number of terms. In Calc 2, you will learn to manipulate these sequences and series and figure out when these sequences and series come to a limit. You will also learn to express functions as an infinite sum of powers of x. On this slide, you're seeing examples of the exponential function and the natural log function. Why are we learning this? Look at the e to the x function. If we stop at the 3 dots, we basically have a polynomial. This kind of series, which we call power series, is an extension of polynomials. And under certain circumstances, we can differentiate and integrate it like we would a polynomial. And that is nice because the derivative and integral of a power x to the n is really easy. And that makes representing a function as a series or power series like this very useful in many contexts. Those are the things you learn in Calc 2. What are the prerequisites? What you need to know to learn Calc 2? This is a list. Algebra, geometry, trig, Calc 1. Let's take one at a time. First, algebra. Algebra is the most important part of calculus. These are the algebra skills and knowledge you need for Calc 2. You need to be very good at algebraic manipulation. Calc 2 moves really fast through the semester. You've seen the amount of material that you need to learn. When your professor, your teacher, your textbook do algebra, there's no time for them to slow down to show you every step of the algebra. You need to be really good at algebraic manipulation in order to follow along. And that's just the follow along part. When it comes time for you to do math, your professor and teacher expects you to be able to do all this algebra correctly and quickly. When they write an exam, they will base the timing of the exam on assuming that you can do all this algebra quickly. Geometry, a little less important than algebra. If you know basic area, perimeter, volume, and know how to do proportions with similar figures, you're good. Trig is more important than geometry. You need to know almost all the trig identities you learned. Now the good news is, if you aren't that good in trig, there's still time to catch up. If you're good enough with algebra. Because then you can apply your algebra skills to the trig that you do know, and then your trig will improve. Calc 1. Practically all Calc 1 skills are needed in Calc 2. I can't think of anything from Calc 1 that's not showing up in Calc 2. Again, because Calc 2 moves fast, your professor and teacher will assume you know whatever was taught in Calc 1, and they're not going to wait. You'll need to do any catching up on your own. Again, the good news is some of these can be caught up. Some of the Calc 1 are absolutely needed, like the differentiation rules and the derivative formulas. But the rest, I'd say, if you're not so good at it yet, you can still work on it while taking Calc 2. So you might think I'm making it like Calc 2 is really hard. Is it? Yes, it is. But check this out. Every year, about 140,000 high school students pass the AP Calc BC exam. That's the high school equivalent of Calc 2. In addition, about 150,000 college students pass Calc 2 at their respective colleges. In total, we're looking at about 300,000 people passing Calc 2 each year. Passing Calc 2 is hard, but it can be done. It has been done over and over again every year. What does it take to succeed in Calc 2? I have a separate video about succeeding in calculus at the link above, so check it out. But here's the list. Number 1 on the list is active learning. Let me show you an example from Calc 1. Let's say you're in Calc 1 class and you're doing related rates. And you're reading a problem and you get to this sentence. It says, the derivatives are negative because... Well, you should stop right there. Don't read on. Just stop right there. Think about why the derivatives are negative. Think ahead about all the explanations and do all the calculations before you read on. Okay, so in this case, you read on and it says because x and y are decreasing. Even if you may not have gotten the correct answer or the correct reason why the derivatives are negative, the fact that you have to think about it and struggle with it will grow your math mindset. And then you get down here and it says Pythagorean theorem. You should be thinking z squared equals x squared plus y squared in your head before reading it on this page. And then down here when it says differentiating each side with respect to t, you should be doing that on your own with pencil and paper. Do that on your own before reading on to see if you have the same answer as the book. And down here when the book is plugging in numerical values, definitely you should stop reading and do it on paper on your own. Don't just copy down what the book says. This is also true when you're watching a video. You should also stop the video, pause it, and think ahead about all the explanations and do all the calculations before you watch it. That's the active learning part. The rest of the skills needed. Practice, practice, practice. I'm sure you've heard this saying before. Math is not a spectator sport. Stay organized and consistent. This is especially true if you're taking an asynchronous online class. You need to fix certain time and date for calculus. For example, 5 p.m. to 7 p.m. Monday, Wednesday, Friday, Saturday are reserved for calculus. Once you fixed a time for like that and you need to have enough time per week, then keep it consistent. Don't let anyone schedule things for you during those times. You have the right to be selfish about your success. Other people, and that includes your best friends and family, need to learn to respect it. Visualize things. We're all visual people. Always draw sketches to visually see what's going on in a math problem. Use technology when needed. Use Desmos. Use GeoGebra. Use multiple resources for learning. Obviously, learn from your book, your professor, and your classmates. That's obvious, but many people miss it. Many people don't read the book or don't exchange ideas with classmates. That's a mistake. Always read the book and always bounce ideas and questions with your classmates. Use online texts and websites. I strongly recommend Paul's online math notes from Professor Paul Dawkins at Lamar University, which is one of the leading universities in Canada. Search on Google for Paul's Calculus 2 notes. You get a website like this. All these materials are included. The notes come with proofs and practice problems and solutions. Use online videos. YouTube is full of calculus videos. Use them all. Of course, I'd say watch my videos, but I'd also like to point you to the MIT OpenCourseware. Google for MIT OpenCourseware, click on Courses, select Mathematics. The course you want is 18.01, which is a combination of Calc 1 and Calc 2. My students also like the YouTube videos of Professor Leonard. These are videos of classroom lectures. Don't forget to practice active learning while watching videos. Press pause often to try to think ahead and do the math ahead of the video. Alright, good luck with Calc 2. Don't forget, 300,000 people successfully complete Calc 2 every year. You should be one of them. Any questions or comments? Leave them in the comments section below. Like, share, and subscribe for more contents. And thanks for watching. Bye.